it's late. You've probably got your IDE open on the other monitor right now. Dark mode engaged. Maybe you're tracking down a bug that's been haunting you for the last 3 hours, or, just scrolling through tech forums while the rest of the house is asleep.
Yeah, that classic late-night debugging session.
Exactly. You're a builder. You're
Yeah.
someone who understands how software is put together, how logic flows deterministically from one line of code to the next. But tonight, we're taking a deep dive into something that it kind of defies that traditional logic.
It really does. It's a completely different way of thinking about computation.
Right. We're stepping out of the static world of ones, zeros, and single frames, and we're talking about how machines are essentially conquering the dimension of time.
Because, we are looking at a fundamental paradigm shift here. The industry is moving away from models that just generate a single frozen slice of reality. They're moving towards systems that attempt to simulate the continuous flow of reality itself.
And the source material for our deep dive tonight comes from some frankly incredible excerpts from the LLM Mastery series. Specifically, a module focused on video generation, the next frontier. Our mission here is to figure out exactly how these models are hacking time.
Which is no small feat, computationally speaking.
Not at all. So we're going to map out the architecture making it happen, look at the honestly mind-bending side effects of that architecture, and then face the very real physical and ethical limits this tech is crashing into.
There's a lot to cover.
There is. So, okay, let's unpack this. For a long time, the AI community was just hyper-focused on images, right? We had image diffusion models doing these incredible things, denoising static pixels to create stunning photorealistic pictures.
Yeah, the progress there was staggering.
It was. But if you take a standard image generator and ask it to make, say, 30 consecutive pictures of a cat walking, and then you just stitch them together, you don't get a video.
No, you get a hallucinatory, flickering nightmare.
A complete nightmare. The cat changes colors. It, grows an extra leg. The background completely shifts.
Yeah.
Why does a model that understands a cat so perfectly in one single frame just completely lose its mind in the very next frame?
Well, it loses its mind because a standard image generator has zero concept of time, or object permanence for that matter.
Right.
It only understands spatial arrangement, where a pixel sits on an X and Y axis in one single isolated moment. So every time you ask it for the next frame, it's just starting from scratch.
So to bridge that gap from a static image to continuous video, the underlying architecture really had to evolve to process that temporal dimension.
Exactly. And the LLM Mastery module points out that the heavy lifting here is being done by extending diffusion models using new architectures, things like 3D UNets or more recently, diffusion transformers.
Which are fascinating.
They are. And the key here is they aren't processing individual pixels anymore. They're processing what the industry called spacetime patches.
Spacetime patches. Okay, I was thinking about this in terms that we, as developers, might use in game design. Think about a voxel.
Oh, that's a good analogy.
Right, because in a game engine, a voxel is basically a 3D pixel. It has volume. It exists in an X, Y, and Z space. Now, imagine taking that voxel and just dragging it through the fourth dimension time.
Yeah, that's essentially it.
So a space-time patch seems like a localized chunk of data that contains spatial information, like, say, the edge of a car's tire, plus the temporal information of where that tire is moving over a specific fraction of a second.
That's exactly how it works.
But, if we map this out computationally, my brain just hits a wall. In a standard image model, just denoising a high-res grid of static pixels requires massive compute.
Huge amounts.
So if we're now taking those grids, stacking them into video frames, and trying to process multidimensional space-time patches, how on earth does the architecture avoid just buckling under the sheer mathematical weight of that data?
Well, the computational burden is exactly why the architecture had to shift toward diffusion transformers. If a system tried to calculate the relationship of every single pixel to every other pixel across every single frame simultaneously.
The math would just explode.
Exactly. It becomes unscalable almost instantly. So the diffusion transformer changes the mechanism. First, it compresses the raw video into a highly compressed latent space. It's not looking at the raw MP4 file, right? It's looking at a much denser mathematical representation of the video.
Oh, I see.
And then it uses the transformer's self-attention mechanism on those specific space-time patches.
Meaning the attention mechanism we usually see in large language models, where it looks at all the words in a sentence to figure out context. They're using that visually.
Exactly that, but applied across time. So the self-attention mechanism allows the model to look at a space-time patch in frame 1 and then calculate its relationship to a space-time patch in frame 15.
Without rendering all the frames in between.
Right, without having to render all the useless static background data in between. By processing patches instead of pixels and using attention to track only the most relevant temporal trajectories, the model just drastically reduces the dimensionality of the problem.
Okay, that makes sense.
It learns that a patch representing, say, a shadow moving across a wall has a specific temporal vector. It's just a highly optimized way of mathematically tracking how things flow, rather than rendering static grids over and over.
And the necessity of handling that sheer computational weight logically birthed the architecture that really shook the industry. I mean, when you combine diffusion models with transformers processing spacetime patches, you basically get the architectural recipe for Sora.
You do. The excerpts really highlight that Sora's major innovation was taking this specific diffusion transformer approach and just applying it at a massive scale.
And one of the most immediate practical results of processing patches instead of pixels, which the sources emphasize, is that it made the model resolution agnostic.
Which is a massive departure from how early models operated. Older AI models were usually trained on fixed tensor grids.
Right.
So if the model was built to output a 512 by 512 square, it was rigidly bound to that structure.
Because the code literally expects a specific matrix size. Like, if you feed it a vertical video, it has to crop it or stretch it to fit the square matrix.
Which completely destroys the training data's fidelity.
Exactly.
Which is why Sora's approach is mathematically profound, because it processes sequences of space-time patches. It just isn't bound to a fixed grid anymore.
That's wild.
The transformer just treats the patches as a sequence of tokens, very much like a language model treats a sequence of words. So you can feed it widescreen cinematic footage, vertical smartphone video, high-res, low-res. The architecture natively understands the underlying structure of the movement, regardless of the framing.
It just ingests and generates any aspect ratio fluidly. But, even with that architectural breakthrough, the source material points to a central technical challenge that is still really haunting the field, like the final boss of video generation: temporal consistency.
The white whale of AI video.
Truly. The excerpts outline this as maintaining object permanence, identity preservation, lighting coherence, and physical plausibility across hundreds of frames. And here's where it gets really interesting for anyone who writes code.
Let's hear it.
As developers, we know how hard it is to maintain state in just a simple web app, right?
Mm-hmm.
You have a user login, you set a session token, you pass variables between components. It is explicit logic.
Right, very deterministic.
So my question is, how on earth is a diffusion model supposed to, quote-unquote, remember the state of a character's face 200 frames later when it's essentially just predicting the next frame's noise?
It's a fantastic comparison because it really highlights the friction between deterministic programming and probabilistic generation. In your web app, state is an absolute truth stored in memory. You query the database, you get the user ID. Right. But in a diffusion model, state is a continuous probabilistic negotiation. The model doesn't, quote-unquote, remember the character's face in a database. Instead, those space-time patches we discussed, they contain contextual history.
Okay.
So as the model uses its attention mechanism to denoise, let's say, frame 201, it looks back at the patches from frame 200. And the mathematically most probable outcome is that the pixels should arrange themselves to look like the exact same face.
But probability implies a margin of error. If it's a continuous negotiation, what happens when it negotiates poorly? Like, if it guesses slightly wrong on frame 40, doesn't that error just compound into frame 41 until the entire reality breaks down and the character morphs into something else?
That compounding error is the exact definition of a temporal consistency failure.
Oh, okay.
And you see it happen most aggressively with lighting coherence. Identity preservation is hard, making sure a blue coat doesn't turn red, but lighting is the true test of a probabilistic model. Human beings are acutely biologically sensitive to lighting anomalies.
Oh, absolutely.
Throughout our evolutionary history, our brains became hardwired to interpret 3D space, time of day, and potential threats entirely through light and shadow.
Yeah, you can spot a bad AI video in like 2 seconds just by looking at the shadows.
Yeah.
It feels deeply unnatural when they move wrong.
Because the physics of light in our reality are absolute. If a subject is lit from the left, the shadow must cast to the right. In a neural network, maintaining that absolute coherence across hundreds of consecutive frames, it requires an astonishing level of temporal tracking.
I can't even imagine the math.
It's intense, and if the model's probabilistic negotiation fails on a single frame, and the shadow drifts even a few degrees out of sync with the light source, the physical plausibility is shattered. The illusion breaks because the math momentarily lost the physics.
Wow. And this algorithmic struggle, this desperate mathematical attempt to solve temporal consistency and prevent those errors from compounding it, has resulted in an unexpected side effect.
Yes.
And honestly, this is the part of the deep dive that feels like we are crossing into straight-up science fiction.
It really is the most fascinating part of the module.
According to the sources, to solve these massive temporal challenges, video generation models are developing implicit world models. Let's let that sink in for a second. Through the sheer brute force process of trying to predict the next frame accurately, the models are actually learning physics and spatial reasoning entirely from video data.
It's one of the most significant revelations in modern machine learning.
It's mind-bending. If we compare this to traditional game development, it's just insane. If I want a car to crash in a game engine, I have to hard code a physics engine. I explicitly define gravity, mass, velocity, collision hitboxes.
All of it.
But the AI model isn't given any of those variables. It's like an algorithm learning to play an incredibly complex video game just by observing the pixels on a screen without ever having access to the game's source code or the physics engine. It just watches millions of videos of apples falling, waves crashing, and cars driving, and it reverse engineers the laws of physics.
You've hit on the fundamental philosophical divide between explicit simulation and implicit understanding. For decades, computer science has been entirely explicit. We write the rules and the machine executes them.
Right.
What we are witnessing with these implicit world models is entirely different. The neural network doesn't know the equation for gravity. It doesn't know what the concept of a hitbox even is. But to accurately predict what a falling apple looks like halfway to the floor in frame 30, it has to implicitly understand that objects fall at a consistent rate.
Right.
To predict how a glass shatters across time, it has to implicitly understand material fragility and kinetic energy.
Because if it doesn't build that internal logic, the compounding error we talked about just takes over, and the glass turns into a puddle of morphing pixels instead of shattering.
Precisely. It builds an internal, highly abstract representation of how the world operates a world model, because that is the absolute only mathematical way to satisfy the objective function of temporal consistency. It can't fake it pixel by pixel forever. To stop the shadows from drifting and the objects from disappearing, it eventually has to understand the rules of the environment it's rendering.
Which is just an absolute triumph from an engineering standpoint. But taking a step back, the fallout of building machines that possess implicit world models machines capable of simulating physical reality with photorealistic accuracy is completely seismic.
Yes. The societal implications are massive.
The LLM mastery excerpts map out a very tense landscape here. We are looking at a collision of staggering computational requirements and heavy societal implications. As developers, we're taught to constantly optimize. We look at O of n squared complexity, and we try to refactor it. But with these models, the compute isn't just a technical bottleneck. It's a massive environmental and infrastructural reality.
The infrastructure required here really cannot be overstated. I mean, training a model to develop an implicit physics engine through spacetime patches isn't like spinning up a few AWS instances to compile a standard app.
Not even close.
No, it requires warehouse-sized data centers packed with highly specialized GPUs running continuously for months. The electricity required to train and then query these models places tangible strains on national energy grids. The tension the sources point out is that we are expending immense physical resources, real electricity, real water for cooling, just to generate synthetic realities.
And those synthetic realities lead directly into the cultural and legal fallout mentioned in the module. They bring up deepfakes, creative ownership, labor displacement, and something they call reality erosion.
That's a critical concept.
And it's important to look at this objectively, based on the text. Reality erosion isn't just about a single deepfake of a politician going viral. It's the slow, systemic degradation of our collective trust in digital media as a standard of evidence.
That is the core of reality erosion. For the last century, photographic and video evidence was considered a foundational truth. If something was caught on tape, it happened.
Right, it was undeniable.
But when photorealistic video complete with accurate lighting and physics derived from implicit world models can be generated by a simple text prompt, that evidentiary standard collapses. We shift from a society that trusts visual evidence implicitly to one that has to treat every single video as a heavily weighted probability of an event.
It fundamentally alters how we process information as a society.
Hmm.
And the source material emphasizes that we can't just engineer our way out of this with better technical patches.
No, because watermarks can be stripped, they can be spoofed, or compressed out of existence. The response has to involve cultural and legal frameworks. The labor displacement in the visual effects industry, where a machine can render a physically accurate explosion faster than a team of animators, or the massive questions around creative ownership when a model generates a film based on an implicit world model built by analyzing a century of copyrighted human cinema. These are not bugs in the code.
Right. They are features of the system operating exactly as designed. Technology is doing what it was optimized to do, but our legal and cultural systems just aren't optimized to handle the output.
It's a massive societal refactoring, and we're basically pushing the code to production while still debating the rollback plan. But what's truly fascinating is that before we even fully solve those legal or infrastructural issues, the technology itself is sprinting toward a hard physical limit.
Yes, the data wall.
Exactly. We mentioned the enormous compute, but there's another resource that is entirely finite. The excerpts point out that because video generation requires vast amounts of pure, unfiltered, real-world data to build these accurate world models, we are actually starting to run out of high-quality training data.
The entire premise of an implicit physics engine relies on observing human reality. It needs millions of hours of drone flights, security cameras, cinema, handheld footage. It needs all of that to intuitively learn spatial reasoning. But there's a finite limit to how much high-quality digitized human video actually exists. We are literally burning through the archive of human history to train these models, and the archive is running dry. So what does this all mean for us? Let's trace the execution path we've taken tonight. We started by looking at how AI broke out of the static image architecture, transitioning from denoising single frames to processing multidimensional spacetime patches using diffusion transformers.
Hugely.
We saw how applying that architecture at scale gave us models like Sora, freeing generation from fixed tensor grids and making it resolution-agnostic. We unpacked the nightmare of temporal consistency, how maintaining state in a probabilistic system forces the model to battle compounding errors in lighting and physics.
The ultimate final boss.
And we saw how that struggle accidentally birthed implicit world models, algorithms reverse engineering the laws of physics just by watching our reality. Finally, we looked at the massive fallout, the energy grid strain, the reality erosion, and the systemic shifts in creative labor, all while we are hurtling toward a data wall where the training material simply runs out.
And this raises an important question, one that the sources kind of lead us to, one that sits right at the intersection of model architecture and our perception of reality itself. If we completely hit that data wall, and the well of true human reality runs dry, these models will inevitably be forced to train on AI-generated video to continue building their world models.
Right, synthetic data.
So when an implicit physics engine is forced to learn from synthetic physics, does it eventually start to hallucinate a completely different version of reality? A reality where the gravity is just slightly off, compounding generation after generation, until the machine's understanding of the world no longer resembles our own.
Man, that is a haunting thought to leave on. A synthetic reality recursively compounding its own physics until it drifts away from us completely. Well, to everyone listening, whether you're finally tracking down that bug in your code or just watching the cursor blink in the dark, thank you for joining us on this deep dive. Keep exploring, keep questioning the logic that shapes our systems, and maybe next time you watch a shadow move across your room, take a second to appreciate the math it takes to render it in real life. Catch you next time.